Okay, so this will be the last video in this sequence. So we want to consider the situations or the cases when Newton method might actually end up failing. Failing in the sense that it does not converge, the sequence of exabands do not converge to a to a value. So we can come up with quite a few examples, but let me explain what is going on. Under what circumstances do we converge? If you just remember the Newton method itself, suppose that you have it can be a cubic or a quadratic. Cubic functions will always converge, so that's usually a common starting point. So suppose that we have this cubic function, we evaluate it at this point. So let me just go ahead and so this is the value at x sub 0. So the method, what it does is it, as you guys all remember, it takes a tangent line and the point where it hits the axis, that would be x1, and then from there we evaluate the value of the function one more time, and then we draw a new tangent line, right? So let me just go ahead and draw a new tangent line in a different color. Maybe I can zoom in a little bit. So zooming in, I draw this new tangent line which will further so this is x2. So the real value that I'm trying to calculate, the root is this number. So this is one of the roots, the root that I want to approximate to. And indeed, we have this nice convergence going on. So this is when things are going well, right? So after a few steps, starting with x0, hopefully not too long, x1, x2, maybe even at x2 or x3, but not too far. Ultimately, it converges, right? So this sequence converges to the true answer, to the true root, say r, for instance, to the true root of the polynomial. All right, but there might be some situations, more pathological cases, as we would call it, where the function, if the starting point is, okay, so because the question is when does Newton method fails, so it's arguably the most common time when it can fail is if you start the guessing point, the starting point is not is different or is far from the root. Here is probably an example. I think it would be better to just work on an example. So consider this other function, again, the x-axis, the y-axis. Suppose that our function has a vertical asymptote somewhere here, let's say, and then our function behaves like this. I don't know, I'm just making up a function here. And then, I don't know, something like that. Okay, so suppose that our function looks like this. So what's happening here is, suppose that our goal is to try to find that point, the root, I should say, right? Not that point. The root. The function has 1, 2, 3 roots, and your goal is to approximate to the desired root. Now, what is going to happen is the following. So if you start at a starting point to the left of this point, so that's the point which we are trying to approximate to. Let's call it r, actually. R, that's one of the roots. Actually, this function has 3 roots, so let's just, okay. So suppose that your goal is to find R or approximate R3, for instance. Well, if you can eyeball it, and you might think that, hey, if I'm close enough, so suppose that if I start at, say, this point, which turns out to be extremely close to the topmost point, then let's see what will happen as a result. So this is your starting point, x0, right? And like we do all the time, we can just draw the tangent line at that point. So when we draw the tangent line, the point where it hits the x-axis, so in this case it is this point, that will be the value of x1, at which point we evaluate it at the function here again. We draw a new tangent line and then so on. Wow, look at that. So if we repeatedly apply this, let me just augment it a little bit. It's hard to visualize what's going on. So the tangent line hits it somewhere there. We evaluate the function again. We draw. So we will ultimately approximate to R2. So even though you started with a point which was fairly close to R3, so somehow the tangent line ended up the approximation gave you the R2 point. In fact, the reason this happened is because the tangent line was relatively flat. So you want to avoid such a situation where the tangent line is relatively flat, and the slope of that tangent line is relatively small. So you want to be as steep as possible. So a better situation would have happened if you could have started with a guess somewhere over here, for instance. All right. Yeah, so that's one concern. Here is a pathological function which is very hard to deal with. So here's an example where our Newton method will actually fail altogether. So if you consider this function, so let's say find roots of the following function, f of x is equal to x to the power 1/3. So which is basically saying this is just the cubic root of x. All right. So for instance, a few values might be interesting to look at. For instance, if you evaluate f of, say, for instance, 1, that will be just the cubic root of 1, which is just 1. F of, say, 8 will be just the cubic root of 8, and that's just a 2, right? Why? Because, just let me show you why. Cubic root of, I can replace the 8 with 2 cubed, which is just 2 to the power 3 over 3, right? So 2 cubed raised to the power 1/3. That's the meaning of a cubic root, which is just a 2. And similarly for f of 27 will end up being a 3, and so on. So for instance, the next one will probably be 64. That would be, so these numbers will just help us sketch the graph of this function. So, and then you can similarly go in the negative direction as well. Long we hold, the function will look like this. So it will be an ever-increasing function. At the point 1, it will take on the value 1. So at 1, it takes on the value of 1, right? So as we, at 8, it takes on the value of 2. It's a little bit far, but let's just do it anyways. So the value of 2 will be hit at that point, say 8 here. Does that make sense? So, and then similarly on the negative side, so this will be -1, and then far on that onto that side, maybe somewhere here. So that will be the -2. So that's a -1. Oops, let's just clean up the mess a little bit, and then so that would be a -8. So evaluated at -8, our function will give us. All right. So therefore, our function will actually look like this. Let me do it in dark color. So it will be looking like this. Let me draw to the best of my abilities. So you can go to Wolfram Alpha website if you want to see how the sketch comes out, but it is something like that. All right, so our goal is to find the root, which is obviously 0, right? Well, analytically, it's very easy to find the roots of this function, but now let's see if we can, if Newton method can actually find that root. So all we need is to implement the standard recursion, x sub n minus f of x sub n divided by f prime of x sub n. All we need is to calculate the derivative of this function. Let me just do it on the spot. F prime of x is simply 1/3 x to the power -2 2/3, and that's just yeah, let's just write it that way, I guess. 3 the cubic root of x squared, if you want, something like that. All right, so if you substitute into our expression, so that will give us the desired recursion formula. So f of xn, so just substitute xn into the original expression. So it's just the cubic root of xn here. And then in the denominator, we will substitute over here. So 1 all divided by 3 cubic root of x sub n squared. Now something interesting happens when you work out the math. So we can move that up to the numerator after some cancellations. So this thing will come out as this, which is -2xn. Now that's interesting, because if we have a reasonable starting point, suppose that we start at the point 1. All right, so if we take 1 as our x0, so we find the tangent line. Oops. All right, so when we find the tangent line at that point, it turns out that it hits the x-axis at the point 2. And when you take the tangent line at 2, it will hit the x-axis again at the point 4. Do you guys see what's happening? Then if you draw a tangent line right here, it will, long behold, the tangent line will hit the axis at the point 8. And as you see, we are going farther and farther away from the actual solution, which is 0. Actually, let's just go ahead and algebraically show that as well. So x1 came out as, so all I do is minus 2 times. So we decided to start with x0 equals 1, and let's see if we can approximate. So 1, so that would be a minus 2. x2 will end up being minus 2 times minus 2, so that's a 4. x3, do you guys see what's happening? 4, that's a minus 8, and so on. x4 is equal to minus 2 times minus 8, that's a 16. We go farther and farther, and it doesn't approximate to the value of 0 at all. In fact, it doesn't approximate to any value altogether. So that's an example where Newton method will fail. There are different ways to fix this as well, but we will not go into that in this course. But I wanted to just let you know that you keep in mind, so there might be some pathological functions like this one where Newton method can fail altogether, and we might end up needing something more advanced, a method or tool to make a correction. Or luckily in some more simpler cases, what can happen is that even though Newton method fails in some ranges, it will end up working in some other ranges, so which is good. And before I conclude here, let me also remind you of one thing. So suppose that, for instance, going back to the initial example, so this function has 3 roots, r1, r2, and r3, right? So that was, let's say, r3. Of course, if I start with a point x0, a guess which is greater than r3, Newton method will approximate to r3. Anytime I start with a point, well, yeah, so different ranges, so what I'm about to say is can give any one of the roots. For instance, picking a point between r2 and r3 does not necessarily mean that it will approximate to r2 or r3, right? So for instance, let me give you guys an example. Suppose that if I start at this point, and after drawing the tangent line, so suppose that's where the tangent line, oops, let's just revise it a little bit, there we go. So suppose that that's where the tangent line hits the axis. So this is your starting point, x0, or let's call it x tilde, x1 tilde, and then guess what happens? So you keep drawing the tangent lines, hey, x3 tilde, and then evaluate it at the original function, it's getting steeper. Yes, wow. So so even though you started at a point somewhere, x0 tilde was somewhere between r2 and r3, we ended up converging to one of the roots, but it wasn't the root that we wanted, right? So you might want to change your initial guess, basically. So initial guess for x0 is, as a result, important. So how can we improve on that? I think the best way to improve on that is, before you start with an initial guess, maybe you can use a website like Wolfram Alpha to actually draw the function and then eyeball where the actual roots seem to look like, where they are, and then based on that, try to find your answer. For instance, if the question is asking for the square root of 40, you need to calculate or answer square root of 40. So what you need to do is, well, because square root of 40 is probably a number between what? It is more than 6, obviously, because square root of 36 is a 6, and it's definitely less than 7, right? Square root of 49, right? So because the answer is somewhere in that neighborhood, so we can, when we start our guess, I think a good guess would be something like 6.5, for instance. All right, so let me just remove that. I hope that was more or less clarifying some of the question marks. Obviously, there's a lot of resources on the web, and also you can check our Blackboard page to get further insight on how to make better guesses so that the Newton method converges faster to the actual solution. All right, hope to see you guys in our next video.